Welcome to my video course on Communications-Based Train Control CBTC.
So today, we're tackling a pretty massive challenge in modern urban transit. I mean, if you've ever waited on a super crowded subway platform during rush hour, you'll definitely appreciate this. You see, with conventional fixed block signaling, trains are actually severely limited in how closely they can follow one another safely. These older systems, they rely on physical track circuits to detect trains inside these rigid, fixed zones. And what happens? It leaves huge amounts of valuable track space completely unutilized. So we really need a system that safely shrinks that distance between trains to absolutely maximize capacity. And you guessed it, that is exactly where CBTC comes in.
All right, here's a quick look at our agenda for today. First up, an introduction to CBTC. 2, the moving block principle. 3, train-borne subsystems. 4, Wayside and control systems. 5, the CBTC data flow. And finally, number 6, our conclusion. Let's dive straight into section 1, the moving block principle, and how we actually maximize track capacity. Picture a train track chopped up into rigid physical segments. That's your traditional fixed block system. A train rolls into a block and the system just flags it, saying, hey, this block is occupied. So the next train coming up behind it has to stay at least one full block away. Now, sure, it's totally safe, but it leaves vast stretches of empty, unutilized space. The modern game changer is the moving block system. With CBTC, we completely ditch those rigid track circuits. Instead, we use continuous radio data to create a dynamic safe zone, literally a moving block, that constantly shrinks and expands based on the train's real-time speed. Because of this, we can safely pack way more trains onto the exact same tracks. It's a massive capacity boost.
Moving right along to section 2, let's talk train-borne subsystems, basically what's happening right inside the train itself. So think of the vehicle onboard computer, or VOBC, as the absolute brain of the train. Housed right inside it, we've got 2 vital subsystems. First is the ATP, the automatic train protection. The ATP is like the strict safety enforcer. It completely prevents overspeeding, and if things get sketchy, it will instantly slam on the emergency brakes. Sitting right alongside it is the ATO, the automatic train operation. Now, the ATO is the actual driver. It regulates the speed, manages opening the doors, all that good stuff. But here's the catch. The automated driver is always, 100% of the time, subordinate to the strict safety parameters set by the ATP. Now, for this whole brain to actually do its job, the train has to know exactly where it is at all times, sort of like a highly precise underground GPS. It pulls this off by reading transponder tags that are installed literally right between the rails. As the train flies over a tag, onboard antennas grab the data, giving it an absolute location fix. And in the spaces between those tags, the train relies on wheel tachometers to measure exactly how far it's traveled since the last tag. It's this extreme real-time precision that makes the dynamic moving block a reality. All right, section 3, Wayside and control systems. Let's step off the train and look at the track and everything beyond it. Down at the physical track level, there's a whole series of Wi-Fi access points. As our smart train moves along, it constantly connects to these access points using mobile radio units. These access points aren't just standalone things. They're hardwired into a highly secure fiber optic trackside backbone network. This backbone streams all the live train data directly up to the zone controller, as well as the automatic train supervision system, or ATS. If the onboard computer is the brain of the train, you can think of the zone controller as the vital brain of the Wayside. It acts a lot like a hyperfast air traffic controller, but for a specific track sector. It gathers incredibly precise location data from every single train in its zone. Once it maps them all out, it calculates what we call a dynamic movement authority. This basically dictates exactly how far, and at what maximum speed, a train can safely travel before it has to stop to avoid hitting the train in front of it. Which brings us to section 4, the CBTC data flow. This is where it all comes together, so let's look at a practical animation of how this works. Okay, let's trace this incredibly fast data journey step by step. Step 1, the train passes a transponder tag and calculates its high-resolution position. Step 2, the train's mobile radio transmits this location wirelessly to the nearest Wayside access point. Step 3, that access point instantly relays the data via the fiber backbone straight to the zone controller. And finally, Step 4, the zone controller processes this against the positions of all the other trains, generates the dynamic movement authority, and fires it all the way back down the chain straight into the train's onboard protection system. Now, what is truly mind-blowing about this process is that this isn't just a one-off message. This entire flow, train to radio to zone controller and back, is a continuous, high-capacity conversation happening multiple times every single second. Up at the top level, the automatic train supervision system manages the overall schedule, while the zone controller handles all the vital safety logic, just constantly updating the train on exactly how far it is safe to proceed. To make sure this constant, vital stream of data never drops, the entire setup is bound together by the Data Communication System, or DCS. Now, because CBTC relies entirely on this continuous data flow, I mean, if the radio link drops, the train just automatically hits the brakes, this central hub has to be built with extreme redundancy. Literally every single piece of vital traffic is duplicated and sent over completely distinct, separate network paths. This ensures a flawless, zero-loss handover as the train blasts past those access points at high speeds. And finally, the final section, our conclusion, the real-world impact of modern train control. Mastering this exact continuous data flow is what gives us the incredibly safe, high-capacity urban transit systems that we absolutely rely on every day. By leveraging these moving block operations, trains can safely run a mere 90 seconds apart from each other. It's the exact technology that enables those fully driverless metros you see popping up in modern cities, all completely governed by zero-loss data networks. At the end of the day, it translates to a safer, faster, and far more reliable commute for all of us. So this technology has clearly already revolutionized mass transit, pushing the absolute physical limits of how many trains we can squeeze onto a single line. But I want to leave you with something to think about. As wireless networks evolve and become even faster, hitting near zero latency, how will real-time data continue to push the boundaries of automated transit capacity in the future? Thanks, we can see in next video.